All right, so this is going to be us working through the worksheet 3 from discussion of principles 1. So we're just going to go through each of the questions. I've written out the basics of the question, but look at the worksheet if you're uncertain about what the question is asking in particular, and you can always check back. So the first question asks you to balance 3 different reactions. So we're going to start with the first one. First one's the easiest of the 3. We've got both of our elements, iron and oxygen, in the product. Each of the reactants is just one of the atoms by itself. So we can look here and see that we've got 3 oxygens to 2 oxygens on the left-hand side. We can't make those even out directly, so we know we're going to have to put a 2 here and a 3 in front of the oxygen. That gives us 6 oxygen on both sides. That's good. Now we can look at the iron. We've got 4 iron on this side, so we need 4 on this side to match. And our top equation is balanced. Okay, moving on to the second one. Here we've got a few more pieces that we have to keep track of. So we can get hydrogen and aluminum on their own, so they're the last things we should balance. So we'll worry about the sulfates. We're going to balance them as a whole because it just makes it easier. We've got 3 sulfates on the right, 1 sulfate on the left. So we're going to need to put 3 here. Doing that gives us our hydrogen number. Now we've got 6 on the left, only 2 on the right, so we need a 3 in front of there to make 6 as well. And then if we look at the aluminum, we already have 2 over here and everything else is balanced. So a 2 out in front of that will balance us off. For the last one, you're not given the formulas directly, you're given the names. The first thing you need to do is convert the names into formulas so you can think about what you've got. So we've got potassium sulfate. Now sulfate's got a -2 charge, potassium's got a +1, so we need 2 of those. Plus barium chloride. Now again, these don't have the same charge. Chlorine has a -1, barium has a +2, so we need 2 chlorines. Moving to the other side of the reaction, we've got potassium chloride and barium sulfate. So we've already dealt with the charges on the other side. Here it's much evener, the +1 with the -1, the +2 with the -2. So then we look at what we need to balance. We've got 2 potassiums on the left and only 1 on the right. 1 sulfate on both sides, 1 barium on both sides, 2 chlorines on the left, and 1 on the right. So if we put a 2 right here, we balance both the potassiums and the chlorines at the same time, and we're finished with balancing. Okay, so that's all there is to number 1. We'll move on to question 2. All right, so for question 2, we've got a question that asks us to calculate the formula weight of glucose. The formula for glucose is given as well, since you're not expected to know that name. So here we've got 6 carbons, 12 hydrogens, and 6 oxygens. So if you go to a periodic table, you'll find the molar mass of carbon is 12.01, the molar mass of hydrogen is 1.01, and the molar mass of oxygen is 16.00. If we then multiply by the numbers, times 6, times 12, and times 6, we get 72.06, 12.12, and 96. And then if we add those numbers together, we get 180.18. Now, that's either in AMU or grams per mole, depending on what we ask for. We're looking at formula weight, so it's AMU for this one. Okay. All right, so moving on. The next 2 questions deal with percent composition. The first one, we're looking at sulfur in sulfuric acid. The second one will be oxygen in glucose, which is why we did question 2. So looking at question 3, the first thing that we need to decide on is what the formula weight of sulfuric acid is. And so if you look at all of the pieces, and I'm not going to walk through each of the steps, what you wind up getting is this is 98.079 grams per mole, or AMU, whichever you prefer. For this step, it doesn't matter. Now we want to know the sulfur, so we need to figure out the mass of the sulfur. So sulfur by itself has a mass of 32.09. Again, we'll say AMU. So now, what we want to do to find percent composition is take the element, the mass of the element, in this case sulfur, times the number of sulfurs divided by the total mass, and then multiply that whole thing by 100 to get a percent. So in our case, we've got 32.09. If we look at the sulfuric acid formula, there's only one sulfur, so we'd multiply by 1, and then we divide by the total, and then multiply by 100 to get a percent. And if you work the math out, you get 32.72%. And that should make a lot of sense, right? The denominator is basically 100, which means you're going to basically get 32% out, right? It's not quite 100, so it's a little bit bigger, but that at least tracks. It should make some sense. Okay, so for question 4, we're going to do it exactly the same way. Just for the sake of argument, I'm going to write in what glucose is here. All right, just so you remember, it's up above, but that's okay. So we need the formula weight of glucose, and again, we did that up above, so we're not going to walk through that again. And again, it's AMU. Now, oxygen, if we go to our periodic table and check, has a molar weight of 16 AMU. So we've got that. So we're going to do exactly what we did up above. We're going to take the mass of the element we're looking at, in this case, oxygen. Then we're going to multiply by the number of oxygens in our compound that we're looking at. And here, we've got 6 oxygens. So we're going to multiply by 6, and then we're going to divide that whole thing by the total mass. So if you work the math out on top, you get 96. Again, we worked that out up above, so you don't actually have to do the math. You can just look back up. And then we multiply the whole thing by 100 because, again, we want a percent. So if you work this out, you get 53.28%. And again, that should make some sense. 96 is just about half of 180, so we get something that's just about half of the mass. It's always good to check to make sure our numbers make some sense. Okay, so moving on. Now we're going to go to a slightly different thing. Now we're going to start working with moles. For the rest of the worksheet, basically, we'll be working with moles. So here, we've got 1.67 moles of lithium chloride. And what I want to know is how many lithium atoms we have in that amount. And so, start with what we know. So, we've got moles of lithium chloride. Now, to get to atoms of lithium, we have to do 2 different steps. The first thing we have to do is we have to get rid of the lithium chloride and get to lithium by itself. And then once we get to moles of lithium, we can go from moles to atoms. So we're going to look at this as a 2-step process. The first thing we want to do is go from moles of lithium chloride to moles of lithium. And then the second step is going from moles of lithium to atoms of lithium. Right? So it's always good to write your units in beforehand. This makes sure that our units cancel out and we're going to where we want to go. And I can do that before I put the numbers in. I don't even have to worry about that just yet. So to go from lithium chloride to lithium in this first step, I need to know the mole-to-mole ratio. So what's convenient about that is we can look at our formula and look at the atom we're looking to look at here. So lithium in this case, and go, okay, in every lithium chloride, how many lithiums are there? Well, there's 1 lithium in lithium chloride. So the mole-to-mole ratio is 1 to 1. That's real convenient because we don't really have to worry about the math there. Cancel out our units. Now we're at moles of lithium. For moles of lithium, we want to get to atoms of lithium. And so here we're going to use Avogadro's number. That's the conversion between moles and atoms, or molecules, or ions. In all those cases, we use the same number, and that's 6.022 times 10 to the 23rd. And that's atoms in a mole. So again, our units cancel out, and we're left with atoms of lithium, which is what we want. And so if you do the math, you get 1.01 times 10 to the 24th atoms of lithium. Okay? So we're going to do the same thing in question 6 here, but we're going to do it with a slightly different compound. So here we're looking for oxygen atoms in 0.35 moles of sodium perchlorate. Remember, perchlorate's a polyatomic you guys have to memorize, so it's just good to practice. So once again, start with the things that we know. We've got moles of the perchlorate here. And again, we know we're going to do 2 steps. So the first step is getting from sodium perchlorate to oxygen. So this is a mole to mole. So COO4. And then the second step is getting from moles to atoms. Okay. Now the nice thing is the second step is going to look exactly the same as it does up here. So I'm going to go ahead and just write it in because I already know that Avogadro's number is going to be involved. So now I just have to worry about this mole-to-mole ratio part. So again, I ask myself the same question. In every sodium perchlorate, in every molecule of sodium perchlorate, how many oxygens are there? Well, we don't have to worry about the sodium or the chlorine, but here in the oxygen we've got 4. So in every 1 mole of that, we're going to have 4 moles of oxygen. That takes care of our mole-to-mole ratio. We check our units. Moles of sodium perchlorate go away. Moles of oxygen go away. We're left with atoms of oxygen. That's what the question asks for. And when you work out the math, you get 8.4 times 10 to the 23rd atoms of oxygen. Okay. So up next is question 7. This is the other thing that we can do with moles. Instead of looking at moles and atoms, we can look at grams and moles. So here we have 18.56 moles of magnesium sulfate, and we want to know what the mass, and we want to know the mass in terms of grams. So just so we know what we're aiming for, let's slide this up just a little bit. So okay, again, you always start with what you know. We know we have moles of magnesium sulfate. I want to go from moles to grams, again, of magnesium sulfate. And so for this, I need to know the molar mass of magnesium sulfate. And I don't know that off the top of my head, and we didn't work it out earlier in the worksheet. So if we think about what we've got here, we've got magnesium, we've got sulfur, and we've got oxygen. So the molar mass of magnesium is 24.276. The molar mass of sulfur is 32.09. We actually used that on the previous page on, what was it, question 3. And the molar mass of oxygen is 16. And then if we look at that, there's also 4 oxygens, so I have to make sure that we multiply that by 4. So if we look at what we get, the first 2 don't change. And this is 64. And then if we add those together, we get 120.366, assuming I haven't done any math wrong. And so we know that in 1 mole of magnesium sulfate, we have 120.366 grams. Units cancel, leave us with grams. And if we do the math, let me check my notes to pull the right number. Here we go, 2234 grams of magnesium sulfate, right? You could also say 2.234 times 10 to the 3rd grams. That's fine, right? Either way. And so with that, we'll move on to the next question. So up next is question 8. So question 8, it has a lot of parts going on to it. I've simplified it for this, but what the question's asking us is, if we have an empirical formula that is C3H4, and we know the compound that we're studying has a molecular weight of 242 AMU, what's the molecular formula of our compound? And so this often comes up because some of the analytical techniques that we use to study compounds just give us empirical formulas. So we have to work backwards to molecular formula. So the first thing we want to do is go, okay, we need to figure out how many times we have to multiply by the empirical formula to get the molecular formula. And to do that, we need to have some ratio between them, but we don't have the pieces that we need as it's written right here. We need to get to some mass value for the empirical formula. So the easiest way to do that is just to figure out what the formula weight for that would be. So we've got 3 carbons and 4 hydrogens. So carbon is 12.01, hydrogen is 1.01, there's 3 and 4, and we're going to round slightly and just say that when we do the math on this and we add it up, we get 40 AMU. It would technically have something out in that last digit, but we're not going to worry about it for the purposes of solving this. And then we now have our empirical weight, we have a molecular weight, we can divide by them to get a ratio between them. So 242 divided by 40 gives us 6.05. And so that number is pretty close to 6, so we're going to call it 6. And so if we want to get to our molecular formula, we take our C3H4 and we multiply it by 6, and so we get C18H24, and that gives us our molecular formula. Okay? All right, and the last question that we're going to go over here is question number 9. So question number 9 gives us a combustion reaction that I've written out up here, and then gives us two reactant amounts. It gives us 15 grams of butane, the carbon compound here, and 2 grams of oxygen. And the question asks, how much CO2 can you make from those two reactants? So this is the start of a limiting reagent problem. So because we have two reactants, we have to figure out which reactant runs out first to be able to figure out how much product we can make. So the easiest way to do this is to do two processes at the same time. So I'm going to start with what I know. I've got 15 grams of C4H10, and I have 2 grams of O2. And so I'm going to convert both of these into moles of CO2. And I'm doing that because one of these will run out before the other one, most likely, unless we gave you a situation where you have exact amounts, which we probably didn't do. So one of these is going to run out first, and so if I convert both of these into CO2, one of the numbers will be smaller. And the smaller number is the number that I can then push forward to get to grams, which is what the question wants. This is one of a variety of ways you can solve one of these problems, and if that isn't the method you use, you learned it differently, that's fine, but that's how I'm going to do it because it makes the most sense to me. So okay, so we need to get to moles of CO2. So the first thing we need to do is go from grams of our respective compounds, whoops, that would be C4H10, not CO, and grams of O2, and we go to moles of C4H10 and O2. So that's going to be our first step. Our next step is going to be to relate moles to moles. So in both cases, we're going to CO2 from whatever we started with. And that's where we're going to stop. Now, once we know which one of these is the limiting reactant, we know which one's smaller, that one will take an extra step after this. But for now, this is all we're going to do. So we can plug in the pieces that we know. We know that in 1 mole of O2, we have a molar mass that is 32 grams, right? 16 times 2. Now, for the butane, I don't know what that is off the top of my head, so we'll just check it real quick. We've got 4 carbons, and we have 10 hydrogens. Carbon is 12, hydrogen's 1, so times 4 times 10. So this times 4 is going to give us 48. This times 10 is going to give us 10. We're at 58. So 58 grams in every 1 mole. Let me get to our mole to mole ratio. And so here we have to look back at our balanced chemical equation. So carbon dioxide has an 8 out in front of it, so in both cases it gets an 8. Our reactants have different numbers, so in front of the butane we have a 2, in front of the oxygen we have a 13, so we put those numbers in. This is why balanced equations are super useful for us, because they allow us to relate compounds like this in a reaction. So then we work out the math, and for the top one we get 1.022 moles of CO2. For the bottom one we get 0.038 moles of CO2. So now again we're looking for the one that is smaller. 0.038 is smaller than 1.022. So we're going to push forward with that one. And so we now need to convert moles of CO2 into mass of CO2. So that's a one-step process. We've got moles. We're going to grams. These are both CO2. In 1 mole, if we think about what CO2 is, CO2 has a molar mass of 44.01 grams per mole. So 1 mole, 44.01 grams, and if we work out the number, we get 1.69 grams of CO2. Okay, so for all limiting reactant problems, this way is the way I would do it. Again, if you have a different way, that's fine, but you're going to work the problem through, figure out which one has less, and then push forward to the answer from there. So hopefully this at least gave you something to look at as you're working through the worksheet. As always, if you have any questions, feel free to ask your TAs, and we'll go from there. Thank you for your time.